We lightly covered types in the last video, but only really to show the importance of where things live in memory. Rust's type system is perhaps one of its most rigorous and powerful features. Understanding it is key to understanding why the language is the way that it is. Today we'll cover the basic types, also known as primitives, that exist within Rust, and what structures we can use to create our own more complex types, also known as compound types. This series has a free accompanying book in which you can find all the details for this tutorial. Check the description below. My name is Daniel. Welcome to Iris. In programming, a type describes what kind of data or values can be used in a particular circumstance. In Rust, we use types to describe variables, parameters, properties, or anywhere else you can have a value, so that the compiler knows what the data at that point will look like inside the running program and how it will behave. This can include where in memory the data lives, how it's represented in memory, and what functionality can be assigned to that data, though we'll cover that last part in a few videos' time. Primitive types are effectively the building blocks of all other types. I think this is an early point in learning Rust that scares off a lot of potential new Rust engineers. You see, Rust has a lot of primitive types. I'm going to show this to you now, but I don't want you to worry about it. You, whoever you are, my dear Rustacean, have already achieved things more complicated than learning this. Don't panic. So, are you ready to see something terrifying that long before the video ends, you're going to have a complete handle on? Here we go. This is how many primitive types there are in Rust, and yes, as scary as it is, you will completely understand this in a few minutes. First, and most importantly, forget this chart for now. There's really only 5 categories that we actually care about. Integers, floating points, characters, booleans, and string slices. We'll go over each of these individually, explain how they work, their variations, and what you might use them for. Before we do, in order to understand those variations, let's very quickly cover binary. Don't panic. No one is expecting you to learn how to count in binary. Counting in binary is fun, but pretty useless. All I want to do is show you how things are represented in memory, because it's going to make all those Rust types make a lot more sense. Humans, mostly, count in base 10. That's numbers going from 0 to 9. You can imagine numbers as a series of columns, where each column represents how many ones, tens, hundreds, etc. there are in a number. For example, the number 123 contains 1 lot of 100, 2 lots of 10, and 3 lots of 1. Each time we increment a column, if the column goes over 9, then we set it back to 0 and add to the next column along. So if we add 1 to 9, it goes to 10, 19 to 20, and 99 goes to 100 because the rollover from the rightmost 9 adds to the next 9, which also causes it to roll over. This counting system is called base 10 as each of those columns is 10 raised to the power of which column it is, starting at 0. 10 to the power of 0 is 1, 10 to the power of 1 is 10, 10 to the power of 2 is 100, 10 to the power of 3 is 1000, etc. Electronics, and by extension computers, can only really cope reliably with things that are on or off though. How do you count with only on or off? Well, what if instead of having 10 possible values in each column, 0 to 9, base 10, we only have 2, 0 to 1, or base 2? This is binary. In binary, our columns are a bit different. 2 to the power of 0 is still 1, but 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, etc. So, if we want to represent the number 13 in base 2, we can see that it contains 1 8, 1 4, and 1 1. 8 plus 4 plus 1 equals 13. Sometimes, when we want to write something in binary and be explicit that that is the system that we're using, we might write OB1101. The OB at the start makes it clear that a number like OB1101 represents 13 and not 1101. Each 1 or 0 is a binary digit, which is where we get the term bit. 8 bits is a byte and can represent the numbers from 0 to 255. Again, I'm not expecting anyone to be able to read this. The reason why a byte is 8 bits has a lot of history, but it basically comes down to character encoding. With 7 bits, you can represent 127 characters, which covers English lowercase, uppercase, numbers 0 to 9, various whitespace, and punctuation, and you still have 1 bit left over for simple error checking. As a quick aside, as a software engineer, you're very likely to also see numbers written in hexadecimal, base 16. This is because hexadecimal is really nice when working with bytes. 1 byte is 8 bits, but it's also just 2 hexadecimal digits. Hexadecimal digits go from 0 to 15, but are represented as 0 to F. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. OXF is 15, and so is OB 1111. The number 255 is much easier to write as OXFF than OB 1111 1111. Both the OB and OX notations work in Rust if you want to write numbers as binary or hexadecimal respectively. You can also use underscores to space out numbers for legibility. Now that you've had that primer on binary, I bet those 12 different integer types are starting to make a lot more sense. The most basic number type in Rust is the U8. This is an unsigned integer represented by the U that is 8 bits in length. Unsigned means that the number can only be positive. It doesn't have a negative sign. You might have already guessed, but this is 1 byte and can hold the numbers 0 to 255. A byte like this can be used for all sorts of things, though one common example is as part of a color. We often represent colors as 8 bits of red, 8 bits of green, and 8 bits of blue, and sometimes 8 bits of transparency. I8 is an integer that can represent both positive and negative numbers, i.e. it's signed. It also only uses 8 bits of data, but instead of going from 0 to 255, it goes from negative 128 to positive 127. You never need to know this, but if you're interested in the mathematics of how it does this, it uses a method called 2's complement. 2's complement, however, is more complicated than I want to deal with in this video, and we don't really think like computers. The easiest way to visualize it is that the leftmost column is the negative version of itself, and all the other numbers are the same. So the number negative 125 can be represented as 10000011, i.e. the number contains one lot of negative 128, one positive 2, and one positive 1. Negative 128 plus 2 plus 1 gives us negative 125. So that's U8 and I8, and now you've probably guessed that for all the other integer types, U means that it can only be positive, I means it can be positive or negative, and the number after is how many bits are available to that type. Now we can build up a little table to show the minimum and maximum of each of these types. Wow, those numbers get big fast. There's still 2 types missing though, right? USize and iSize. In this case, the size is also acting as the number of bits. However, unlike the other integer types, the size of size is variable. Rust is a compiled language, meaning that the code that you write in Rust is transformed into instructions that a CPU can understand. CPUs are all different, but they typically follow some given architecture. For example, if you're watching this video on a Windows or Linux desktop, the architecture of your CPU is probably x86-64. If you're watching this on a Mac or mobile phone, then the architecture that you're using is probably an ARM64. When you compile Rust, it will compile into an instruction set for the architecture your machine uses, though you can explicitly tell it what instruction set to compile for if you want to build it on one architecture but run it on another. x86-64 and ARM64 are both 64-bit architectures, so when you build for these machines, the size in USize and iSize becomes 64. However, if you were to compile for, say, a Cortex M0 microprocessor, then the instruction set would likely be thumb1, which is 16-bit, so the size in USize and iSize becomes 16. Which integer is right for you? You might think that the obvious thing to do would be to use the largest possible integer types. For example, you can fit pretty much every whole number you could possibly need into an I128, so why would you use anything else? There's 2 things to think about. First, what is the intended use of the number? And second, what is the architecture of the machine you're running on? In software engineering, a number is never just a number. It represents something. As we mentioned earlier, colors are often, but not always, represented as 0 to 255 for each of red, green, and blue. This means that a U8 is the best way to store these. If you combine those 3 values with another 8 bits for transparency, then you have 4 lots of U8, which could be represented as a U32. U8 is also a good size for representing a stream of Unicode characters, which is where we get UTF-8, the default encoding for Rust strings. For larger, more arbitrary numbers though, you still may not want to use the largest integer types. While you can use integers that are wider than the architecture that you're running your program on, like using an I128 on a 64-bit machine, mathematics with those numbers will be slower. The CPU can only process so many bits at once, so when it has numbers larger than that, it has to do multiple rounds of processing to achieve the same result as it might have done with fewer if those numbers were stored in smaller integers. You might then think that the best thing to do is use a usize or isize if you don't really care about how big the number can get, and that's fine, and I often do this, but now you have to bear in mind that the behavior of your program may no longer be consistent on different machines. A usize on a Mac is going to cap out at over 18 quintillion, but on a Cortex-M0 it's a mere 32,000. By default, when you write an integer and store it in a variable, Rust will play it safe and use an i32 as it doesn't know what you might want to do with the number. An i32 will fit inside most CPU architectures without needing extra work and allows negative numbers. However, it is more idiomatic to be intentional about the types that you're going to use. My methodology here is roughly, does this number represent something of a specific size like a color or ASCII character, in which case use that size. Is this number going to be used to access an array, in which case it kind of has to be a usize? Do I need something huge, computational cost be damned? Then a U128 or I128 is going to be the best way to go. Am I more concerned with speed than consistency, in which case a usize or isize? Otherwise, 32-bit and 64-bit integers are probably fine, especially if I know what my code will run on. You can specify what type of number is either by annotating the variable you're putting it inside, or if that's not possible because you are, for example, passing the number straight into a function that could take many number types, you can write the type at the end of the number. A brief note on type conversion. You can convert between integer types in several ways, which we'll talk about more later, but I wanted to quickly go over some code from the last video. In the bonus section of the last video, we got the number of milliseconds that had passed since midnight on the 1st of January 1970, and then immediately used as usize. The reason for this is the number of milliseconds since that date is approximately 1,700,000,000,000 and is returned as a U128. We wanted to use this as part of a calculation to work out an index into an array, and indexes in arrays are always usize. If you were to compile this program on a 32-bit architecture, then the number of milliseconds is greater than what would fit into a usize, which would be just over 4 billion. When going from a larger size to a smaller size, in this case from a U128 to the equivalent of a U32, it simply cuts off the front of the data, leaving the least significant bits. We've covered 12 different ways of storing whole numbers in Rust, but there are only 2 ways of storing numbers with decimal points, F32 and F64. Floating point numbers are things like 0.123 or 1.23 or 123 point nothing. They're called floating point because the decimal can move around. Your immediate thought here might be that you should use F32 on 32-bit systems and F64 on 64-bit systems, but actually, this isn't the way to think about these numbers. I literally only discovered this while writing this chapter of the book. To explain, floating points are not perfectly accurate. The bits of a floating point number are broken into parts: a sign, positive or negative, an exponent, and a fraction. Without going into too much detail on floating points, this gives us a way of expressing very large numbers and very small numbers, but not every number in between. After all, there are an infinite number of numbers between 0 and 1. Imagine using a floating point number to represent money. Someone comes into a store to buy an item that costs $520.04. Somehow they have a coupon for $520.02. The remainder that they need to pay is 2 cents, right? If we express this in code using floating point numbers, we don't get a perfect 2 cents. Instead, if the currency you're representing uses hundredths for its minor currency like US dollars or British pounds, then you can and maybe should represent the total number of that, e.g. cents for dollars and pennies for pounds, using integers instead. So when should you use floats? Floating point numbers are great for more abstract mathematics where perfect precision isn't strictly necessary. For example, vectors, matrices, and quaternions, which are often used in applications like video games and scientific models. As to which you should use, you might think that it comes down to architecture again. For example, a program targeting a 32-bit architecture should maybe use an F32, and 64-bit architecture should prefer F64. But if that's the case, where is F-size? Actually, 32-bit architectures are usually designed to support 64-bit floating points just fine. The difference between F32 and F64 is that regardless of architecture, F32 is about 30% faster and F64 is more fine-grained. To decide which to use, you just need to decide between speed and accuracy. In Rust, we have a special type that represents a single character called char. I say char, some people say car. Unlike stud though, I'm not changing my ways on this one. I'm an old man and I'm dying on a weird hill, deal with it. Char is always 4 bytes, 32 bits in size, and can be any valid Unicode scalar value, which is to say any character in Unicode that's not a control character. In Rust, a character is always written between single quotes, whereas a string literal is always written between double quotes. You can use any valid Unicode character, whether that's uppercase or lowercase English letters, numbers 0 to 9, white space characters, word characters from languages like Chinese and Japanese, emoji, or anything else that's a Unicode scalar value. We usually use characters in relation to finding things inside other strings. You can also turn strings into a collection of characters and vice versa. However, it's important to note that a character inside a string may not take up 4 bytes. For example, English letters and numbers only take 1 byte because of how strings are encoded. However, once turned into a character, they will take up 4 bytes. There is only one Boolean type in Rust, bool. It represents true or false. We often get Boolean values through the use of comparisons between values. For example, is A equal to B, or is C greater than D, etc. Boolean values are usually reserved for if statements, and this is a good thing to look out for, as finding them elsewhere might be a sign that the code isn't written in the best way. For example, functions almost never need a Boolean parameter. This is usually a sign that you probably should have written 2 functions. Our old friend, the string slice. The type for a string slice is struct, but you'll never see anything with the struct type. You will usually see this as a reference to a string slice, &struct, which makes it unique amongst the primitive types. Struct should always be a UTF-8 encoded string, which means that the length of a string in bytes may not necessarily be the same as its length in characters. For example, and don't worry about the code yet, the character that represents my cat's name has a length of 3 bytes when encoded as a string, but the string is only 1 character long. It's also worth remembering that when you turn a string into characters, each of those characters will take up 4 bytes of memory, even though inside the string, they might have only taken up 1 byte. Again, don't worry about the code here, this is just to show the size. The size of a string slice depends on what's in it, which is why you won't ever see it on the stack. String slices live in either the compiled output as string literals or on the heap inside of a string. A string slice reference is made up of 2 pieces of data, a pointer to where the string starts and a length, both of which are of known size, but depend on the system architecture. Fun fact about that reference though, you might wonder, if it's just a pointer and a length, does that mean you can have a reference to a string slice that exists inside another string slice? And the answer is yes. Just be careful when taking a slice inside a slice to make sure that that sub-slice is a valid UTF-8 string. Arrays are a collection of a single type. You might see arrays in 2 forms, either as a sized array on the stack or as a reference to another collection, also called an array slice. When sized, arrays are annotated with the type open square bracket t semicolon n closed square bracket, where t is the type of every item in the array and n is how many there are. For example, here's an array of exactly 5 chars. This is going to exist on the stack. When referenced as an array slice, you don't need to specify the size because, just like with references to string slices, the reference not only contains a pointer to the underlying data, but also contains the size. We write this in the form ampersand square brackets t, where t is the type of every item in the array. You can access elements inside the array directly by using an index value between square brackets. In Rust, indexing starts at 0 and the type of the index is always a U size. Tuples are similar to arrays in that they're a collection of items. However, each item in the collection can be a different type. This adds some flexibility, but also some restrictions. For example, you can iterate over each item in an array, but not in a tuple. Tuples are written between brackets and are only considered the same type if the types inside the tuple exactly match. Another difference from arrays is how you access a single item in the tuple, which you do with a dot, followed by the number of the element that you want. Again, this starts from 0. There is a zero-length tuple that is Rust's way of representing nothing. We call it the unit type. It's 0 bytes, does not exist on the stack at runtime, and unlike other languages with types like null or void, cannot be used interchangeably with other types. You might use this type in conjunction with generics, which we're going to come to in a bit. Structs are similar to tuples in that they're a type made up of other types. Unlike tuples though, they're named, they have to be defined, and that has to happen outside of functions. There are 3 types of structs: structs with named fields, tuple structs, and unit structs. As we just covered tuples, let's quickly talk about tuple structs. They look a bit like they're simply named tuples, and indeed can be accessed in the same way. Similar to tuples, this kind of struct can be accessed with a dot and a numbered value. However, unlike tuples, structs have a concept of visibility. Unless explicitly marked as public, the fields of a struct are only accessible in the module in which they're defined, or its descendants. We'll talk more about modules later. However, to make the fields of a struct public, you can simply mark them as pub. You don't have to make every field public though, if you want some parts to be public and other parts to be private. Named fields work pretty much the same as tuple structs, except instead of having a numbered field, it's named. You can access the named field with a dot and the name. Similar to tuple structs, fields must be explicitly marked as public in order to be accessible outside the module they were defined in. Unit structs are an interesting case that you probably won't find much use for until we get into more advanced Rust and some of the cooler patterns and idioms that we use. Like the unit type, a unit struct has no value and no size. They're most commonly used as a marker, but you can also add functionality to them via traits. Enums are for when you want to represent one of a finite number of possible values. For example, say we want to represent the colours of a traffic light, which could only be red, amber, or green. Many programming languages have this concept of enums, but what makes Rust enums especially awesome is that the variants can additionally contain values. We've actually already talked about 2 such enums, option and result, which are 2 of the most important and widely used types in the entire ecosystem. We'll talk more about them when we talk about generics shortly. As an example though, enum variants can be structured in either a tuple style or a struct style. In terms of memory usage on the stack, an enum will always take up as much space as its largest variant, regardless of which variant it actually is. Generics in Rust allow the creation of entirely new types at compile time by combining different types together. We've talked a bit about option and how Rust uses it to represent some value or none. Option is an enum with 2 variants. It's literally just this. Note that after the name of the enum we have a T in triangle brackets. The triangle brackets express that this enum has a type, or sometimes types, that can be decided later. The T is just a marker for that type. For example, say we want to create a type that represents either a single character or nothing. We can use the generic option type to build option char. When we specify the value as some character, Rust can infer that type. If it's none though, we'd have to specifically tell the compiler what the type is, either through a type annotation or other means. Normally, when accessing variants of an enum, you must use the name followed by the variant, e.g. option : some are. However, option and result are so ubiquitous that their variants are globally accessible anywhere in Rust. Result is another generic we've covered before, which usually represents either the success or failure of a function. It has 2 types that can be decided later. T, which should represent the type of data that you expected to get back, and E, which will be the type of the error. We'll talk more about functions in a later video, but in order to explain result in context, this example shows the fully described result type as the return type of the function, which is how we'd typically use this enum, though you typically wouldn't use a string as an error type, and we'll talk more about that later when we get into error handling. When we start talking about adding functionality to types, we'll talk about how you can restrict what types are allowed to be used in generics through the use of trait bounds. That is almost everything you need to know about types. The main things we're still missing are ownership and traits, but we're going to come to those when we talk about functions. The main things to remember are we have our primitive types that represent binary data. There's a lot of choice here, but that's a good thing. We can represent more complex types with compound types. We can do the type equivalent of fill in the blank using generics. And we talked a little bit about the most common generics, option representing something or nothing, and result representing a success value or an error. In the next video, we're going to talk about controlling the flow of our program with branches and loops, as well as pattern matching and expressions, which are two of my favorite features of this language. If that interests you, don't forget to like and subscribe. Between now and then, why not try experimenting with your own types? And I'll see you next time.